Sometimes it needs 2 clicks. Okay, it's working now. Okay, so because of the double equivalency, we have to write number 2. You don't have to do anything, but you have to write, now show that delta equals 5 epsilon over 4 works by reversing the steps from above. And you do not have to do it. That's it. Do we have other questions here?
So for the second part, so we just write that and
that's it. Full stop. That's where it ends.
Okay, I see.
Do you think we need to look at another?
I think one more might be helpful.
Okay.
Yes.
Perfect. And then we can look at one quick numerical example. Let's say, I don't remember which problem we did last time, but let's look at limit as x approaches -2 from 3x plus 5 equals -1. Let's check. -6 plus 5, -1, check. Okay. Can anyone dictate what I should write?
Would it be for every
Epsilon positive
greater than 0?
Perfect.
That backwards e symbol? What
yes,
was that called?
There exists. I will find.
There exists. I will find a delta great positive.
Very good. Such that.
So
now this is the mechanism that says if I choose x close to a, f of that x will be close to epsilon. That's all it means. That's it. And the reason we write 0, this piece positive, we know the absolute value is positive. Why do I need this? Just to make sure that it does not equal to, that I do not pick x to be a. That's why this is here. No other reason. There is no reason for me to write that the absolute value is positive. Everybody knows that. But it says that it's not equal to. That's all it means. Okay, what do we put in the absolute value?
X plus 2.
Very good. It has to be less than delta. The distance between x and -2 has to be less than delta. And if I choose x close enough to 2, to -2, in the sense that it's less than, the distance is less than delta, what has to happen for sure?
F of x.
3x plus 5. Must equal -1.
Very good.
Is less than epsilon.
That's it. You got it. Perfect. We start here. So this is 3x plus 6. This is not cheating. I'm looking to see ahead, what am I after? This is what I'm after. So what do I do?
Take 3 out. It'd be
good.
X plus.
Excellent. You cannot divide before you write one more step. It has to be one more. What is the next step that I have to write and I cannot skip?
The absolute value of 3 times the absolute value of x plus 2.
Yes. You can say, but this is silly. No, it's not. You are showing that you are applying the property of absolute value of a product, that equals the product of absolute values. Now you have to write this, and only now you can divide. What do I divide by?
Three.
Finally, what do you think delta is? And don't say anything just yet. Just compare. Compare this to this. And you'll know what delta is. Just compare. So what is delta?
Epsilon over 3.
Done. And of course, number 2, you know what to write. Anything else? Are we okay?
I'm good.
Perfect. Now I would like to show a numerical example. Where are you guys? I lose you and I click on other windows. I lose you. Okay. So can I go back here? No, I cannot go back. But I can go back here.
Could I just ask one quick question?
Yes.
So we just finished this problem, right? Like we're doing our homework. You just square off the answer like that, or do you want the sentence show delta?
Oh, you have to. I was just lazy because I want to move on.
I just want to double check.
No. You have to show both, yes. But you don't have to act on the second one. Just write that sentence, yes. So I like us to look at these graphs, the numerical examples, just for 1 second. So for example, this is the first problem in 2.4. And it says, use the given graph to find a number delta such that if the absolute value of x minus 1 is less than delta. So can anyone give us what is the number we are looking at? What is A?
It's 1.
Exactly, right here. Then f of x minus 1 is less than 0.2. Can anyone tell us what is the limit here in this figure, in this graph?
1.
Of course. Can anyone give us what epsilon is? Because it's already given to us. But see, it's 1 plus 0.2, 1 minus 0.2. So the limit is 1. For every epsilon, they want specific epsilon now. They give us 0.2. So when epsilon is 0.2 above, I get this number. When epsilon is 0.2 below 1, I get this number. So now the question is, and we discussed that, but it's okay if you forgot. Which one do I pick? So for a second, yes, go ahead.
The lesser one? So
Exactly. Because look, if I use the smallest one, I will have this interval, symmetric interval. But if I use the bigger one, I have this interval. And I could possibly choose x here. It meets the function. And look, f of x is here. And the distance between 1 and f of x is way more than epsilon. That's the reason why I have to choose the smallest. So then what is delta in our case?
0.7.
Delta has to be the difference between this and this, or the difference between this and this.
0.1.
One more time, what is it?
0.1.
Exactly. This is the difference. So it's 1 plus delta, 1 minus delta, 1 minus epsilon, 1 plus epsilon. Okay. Let's also look at this one. So they're giving us the function. Obviously, A is what? Good. The limit is what?
2.
Exactly. We have the square root of x. When x is 4, the limit is 2. Can anyone give us epsilon?
0.4.
Perfect. So now we have to establish what is delta. Okay? So when for a particular value, I get the square root of x to be 1.6, and then for a particular value, I get the square root of x to be 2.4. I'm going to write this, and then I'll stop sharing. So the square root of x equals 1.6, and the square root of x equals 2.4. We don't know what this is. We don't know what this is. But when I have the square root of 4, I get 2. The square root of blah, I get 1.6. The square root of blah, whatever, blah 2, blah 1, the square root of blah 1 is 1.6. The square root of blah 2 is 2.4. I can determine these. So how do I solve these equations?
We square both sides.
Of course, it's a radical equation. I have to square both sides. Can anyone give us x here? And can anyone give us x here?
The first one is 2.56. And the second one is 5.76.
Good. So remember what we have. We have 4 in the middle. I have 2.56 here, and I have 5.76 here. Which will I consider as being delta? And how do I get that?
Comparing both distances and picking the smaller one.
Good. So 5.75 minus 4 is 1.75. And 4 minus 2.56 is 1.46. Correct my mistake, my numbers, my errors anytime. I'll give credit for that. Because I may see something you don't. I don't. You may see something I don't.
1.44.
You're right.
It shouldn't it be 1.76?
Oh, this was 6. Yes. So, what is delta?
$2.56.
I'm sorry. What do you mean?
Oh wait, no, the number is 1.44.
I completely agree. So for epsilon, we had, I'm sharing my screen again. For epsilon 0.4, we get delta to be 1.44 for this particular function in this particular situation. I think we had enough of that. Are we okay?
Yes.
Okay, so let's continue. I would like to continue with 2.5, continuity. Of course, if you find something else that you want to discuss in class, I'm more than happy to. Okay, so what do we mean by continuity? So here are a few examples. Here's another example. Here's another example. Here's another one. And one more. So let's analyze the first graph. Can I say that this is a continuous, smooth function?
Yes.
continuous, smooth function. Polynomials are like that. Exponential, logarithmic on its domain, sine, cosine. What about this situation? Is this continuous? This has a jump discontinuity. What about this? Is this function, or are these functions continuous? This one is not defined at this point, and this one is, but not here, somewhere else.
No.
No, they're not. They are called removable discontinuities. Removable. I can, for one or in this case, one value or a finite value, I can rearrange this. I can create a new function, and this is, I'm going to fill it in because it's just one point. Here I cannot. The same thing here. It's a removable discontinuity. Okay, now, what about the last one? Is the last one continuous everywhere? You can say, yes, it's continuous between negative infinity and this number, and between this number and infinity. But I'm asking if it's continuous everywhere.
No, because
No.
of the asymptote.
Very good. It has a vertical asymptote. This is called infinite discontinuity. So this function is not continuous because it has an infinite discontinuity. This one has a jump, a discontinuity type jump. These two have removable discontinuities. This is a nice one, continuous. So polynomials, rational, trig, radical are all continuous on their domain, or domains if you want. Any combination, addition, subtraction, multiplication, division, function composition, any combination of continuous functions is, what do you think?
Continuous.
Absolutely, thank you very much. Any combo, if I add two continuous functions, I create a new continuous function. If I multiply two continuous functions, I will get a new continuous function. If I subtract, multiply, function composition, yada yada, they will all be continuous. If I multiply by a constant, I will get a continuous function. Okay. Continuity on an interval, but before that, continuity, very important definition. Continuity at a point. So let's take a look at this little graph. Here's a graph of a function. I'm talking about point A. Is this function continuous at point A?
Yes.
Yes. Three things have to happen. The limit from the left, the limit from the right, and the function value at that point all have to exist and be equal to each other. So here's the definition, very important. Limit, S, of course, this is A, right? And this is L. The limit as x approaches A from the left of the function, from the left, must equal the limit from the right of A, and must equal the function value at A. This is continuity at a point. All three have to exist, and they have to be equal for a function to be continuous at a point. But what about continuity on an interval? On an interval. So if I want this interval, of course, around A, what has to happen here for me to say to you, this function is continuous on this interval? What has to happen? Any function is continuous on an interval if it is at each and every point. What? Continuity on an interval if a function is at each point on that interval. It is what?
Continuous?
Of course. If it is continuous at each and every point on that interval, the function is continuous on the entire interval. I would like to just give the definition for removable discontinuity, and then I'd like to look at some problems. So we talked about this removable. It's removable because the limit from the left and the limit from the right are the same. The only thing is that they are not equal f of a. So this is removable. The limit as x approaches a from the left of the function indeed equals the limit of f of x as x approaches a from the right. But the only problem is that it does not equal f of a. It does not. This is called removable discontinuity. One last thing is something we